So, last talk of this morning session and sadly of this whole workshop is Professor Olya Mandelshtam from University of Waterloo, and she'll talk about a new tableau formula for Macdonald polynomials via the ASEP and TAZRP.
So thank you very much for the introduction, and thank you to the organizers for this conference and for the opportunity to come to India. So my talk will be focused on presenting Macdonald polynomials entirely from a combinatorial perspective by giving an explicit formula for their coefficients through the interpretation of the particle processes, the ASEP and the TAZRP. So the TAZRP is a zero range process. So a brief overview of what I'll talk about. So the Macdonald polynomials are a family of symmetric functions, which are a basis for the ring of symmetric functions in parameter Q and T. And we've heard about them a few times this week. So there's a certain transformation called plethism that sends the p lambda to the modified Macdonald polynomial, which is a combinatorial version of them with positive integer coefficients. And these polynomials have a very beautiful connection to the ASEP and the TAZRP. So the ASEP is asymmetric simple exclusion process. TAZRP is totally asymmetric zero range process. And both of these we got to hear about in the previous talk by Chiba. And so the connection is that when we set all parameters in the Macdonald to 1 except for the t, then we get the partition function of the ASEP. And I'll explain later what I mean by partition function in this case. And analogously, when we set the q to 1 in the modified Macdonald, then we get the zero range process with spectral parameters. And then these two, so the ASEP can be thought of as a fermionic version of the TAZRP. And so we've been working on finding combinatorial formulas that exhibit this relationship. And so we just heard about the multi-line Q formula that lets us compute stationary probabilities for the ASEP, which was discovered by James Martin. And soon after that, with Sylvie Cortell and Lauren Williams, we were able to extend that formula to incorporate the full parameters of the Macdonald polynomial. And then on the other side, we found this formula with Arvind, Ayyer, and James Martin that on one hand gives us the stationary distribution of the TAZRP, and on the other hand, it gives us the full modified Macdonald polynomial. And we call this a quin or a Q inversion tableau formula. However, there's no explicit relationship between these two. I mean, the objects have a similar flavor, but we can't form an explicit connection between them. So recently, my goal was to find a formula over here that comes from the Q inversion formula. So that's what I'll be presenting in my talk. So superization is a combinatorial way of viewing plethism, and it allows us to obtain a tableau formula for the p lambda that comes from the tableau formula for H using the same statistics. And this formula also naturally reflects the dynamics of the ASEP and the TAZRP. Okay, so let me review what these models are. So first of all, so my Macdonald polynomials are in type A, which means that everything I'm doing is on a circle. So we fix a circular lattice on n sites, and we choose a set of particles which are given by a partition lambda. So we just arrange the particles in weakly decreasing order. And then we fix a parameter t between 0 and 1. And so the ASEP, which we just heard about, has states that are all possible rearrangements of the particles on the sites of the lattice. And so we can think of these rearrangements as compositions of lambda, where we just assume they're on a circle. So we can chop the circle at an arbitrary spot and then read the state clockwise. So this corresponds to 2, 0, 3, 2, 1. So that's my. And then transitions are swaps of adjacent particles. And the asymmetry is given by this parameter t. So in particular, when t equals 0, stronger particles can only move in one direction. So that's the ASEP. Okay, and then on the other hand, the zero range process is the bosonic version of this model. So now we don't have the restriction that there's at most one particle per site. So my states are multi-set compositions that rearrange to lambda. And again, I read the state clockwise by chopping the circle. So this is the first site has particles 2, 2, then empty, then 3, 3, 1, and then 2, and then 1. And my transitions are now given as follows. So particles can only jump in one direction, so they can only jump clockwise. But the jumping rate depends on a parameter t. And essentially, the rate of a particle jumping is going to be t to the power of the number of particles larger than it in priority. So the particle with highest priority will jump with rate t to the 0, and particles with lower priority will have to have their jump weighted by some t analog. And then we also, in this model, have spectral parameters. So each site j, has associated to it a parameter xj. And so a jump from site j will also come with rate xj inverse.
We'll have a stupid question. So do I get it right that you have, what, n particles, and each of them is labeled by some number lambda, and this label tells you the sort of the priority?
Yeah, so we have some set of particles which are given by integers. So the larger integer is a heavier particle. We can think about it that way. So the heavier particle has priority over the.
Okay, got it. Thanks.
Yeah. And the same in the ASEP. So the larger labels correspond to higher priority. Okay, and so this model was first studied by Takayama in algebraically, and then Kuniba, Maruyama, and Okado have studied several related variations of this model, where we can have multiple particles jumping at a time, and other variants like that. Okay, and then. Yeah, so if we set t equal to 0, then the transitions become such that only one particle can jump from each site, and it's always going to be the largest particle. Okay, so now let's briefly talk about symmetric functions. So we have a family of commuting variables, the xi's, and then let's take lambda to be the ring of symmetric functions in these variables. So a function is symmetric if it is invariant under permutation of its variables. And so we have a standard inner product on this ring. And so there's several natural bases for lambda, and these bases are all indexed by partitions. So for example, the monomial symmetric function gives us the most basic building blocks of a symmetric function. So both of these are examples of monomial symmetric functions. and the index lambda tells us the exponents of the variables in those building blocks. And then we have the power sum symmetric functions. And there are several other bases, but our favorite basis is, of course, the Schur functions. And it's our favorite basis because it is the unique family of polynomials that is upper triangular with respect to the monomials, and it's orthogonal with respect to the inner product. So that's how we define them. However, this definition does not actually give us a way to write them down, so it doesn't give us a formula for them. So now let's take our ring of symmetric functions with additional parameters q and t. So now we have an inner product with q and t that specializes back to the standard inner product when q equals to t. And Macdonald introduced these p lambdas, so the symmetric Macdonald polynomials, as a direct analog of the Schur functions in this ring. So they are upper triangular with respect to the monomial basis, and they are orthogonal with respect to this the inner product in q and t. And so these are called Macdonald's triangularity and normalization axioms. And here's an example of one. So as you can see, the coefficients of the monomials are some rational functions in q and t. And then it looks like each coefficient is some power of 1 minus t divided by some difference of q's and t's. And then what's left is a polynomial with positive integer coefficients. And so Macdonald polynomials generalize many other symmetric functions that we heard of this week. So Schur functions at q equals t, Paul Littlewood at q equals 0, q Whittaker at t equals 0, and then we also have Jack polynomials in a certain limit. So now the modified Macdonald polynomials are obtained from what we call probabilistic substitution. And the notation for that is these brackets, this bracket notation. So I'll go into more detail about that later in the talk. And here are a couple examples of the modified polynomial. So you'll notice that their coefficients are positive integers, or are polynomials that have positive integer coefficients in q and t. And not only that, they're also Schur positive. So here I gave the expansion of them in Schur functions. And it's actually it's still a very big open problem in algebraic combinatorics to find an explicit interpretation for these coefficients in this Schur expansion. Okay, so these are the modified Macdonald polynomials. So now many people have tried to come up with combinatorial formulas to understand these polynomials. So first of all, let's talk about the combinatorial formula for Schur functions. So we can, the nicest way to define or compute a Schur function is in terms of semi-standard Young tableau. So a semi-standard tableau is a tableau whose shape is given by a partition lambda, and then it's filled with integers such that the rows are weakly increasing and the columns are strictly increasing. And so if we write out all the tableau satisfying this condition, and then associate a monomial weight to each tableau, where we're just counting how many integers there are of each type. So for example, here we have 2 1s and a 2, so that gives us the monomial x1 squared x2. So then we get the Schur function corresponding to that shape. And it turns out that there's a beautiful formula for the modified Macdonald polynomial that is also in terms of fillings of tableau, except now we have these additional parameters q and t. And so we can think of this as T counting the violations of the row weakly increasing condition, and the Q is counting the violations of the column strictly increasing condition. So now instead of having these restrictions on the rows and columns, we remove the restrictions. So we sum over all possible fillings of this shape, and then we count the violations of the restrictions with these parameters. Okay, and so there's a standard way of interpreting the plothistic correspondence between P and H in terms of a certain non-attacking condition on these tableaux. So this interpretation gives us a formula like this. However, this is not the nicest formula in terms of interpreting the coefficients, because we have this kind of ugly prefactor here, which is some rational function in Q's and T's. Okay, and then there are also other formulas for these. So there's a quantum Alkovach model that is type independent. So Macdonald polynomials come in different Lie types. And then also there are some formulas through integrability. So notably Borden-Wheeler and Garbali-Wheeler and these Agarwal as well. Okay, so how are these connected to the ASEP? So let's define this PR tilde to be the unnormalized stationary probability. And then the partition function is going to be the sum over these unnormalized probabilities. And we choose our normalization so that these unnormalized probabilities have some kind of combinatorial meaning. And we call them the ASEP polynomials. And so there was this amazing result by Cantini, Dehere, and Wheeler, which found that the ASEP polynomials are specializations of certain non-symmetric Macdonald polynomials that that correspond to permuted basement Macdonald polynomials. And the partition function is a specialization of the symmetric Macdonald polynomial when all parameters are set to 1 except for T. And T ends up being the same parameter of the asymmetric hopping rate as the ASEP. And then James Martin was able to extend the multi-line Q formula that we just heard about from Chiba to incorporate this T parameter. And these two results motivated us, so Lauren Williams and Sylvie Cortell, motivated us to try to put in the xi's and the q into the multi-line Q formula to get the full Macdonald polynomial. And so we were able to do that. So let me explain how this works now. Okay, so first of all, I'm very lucky that Chiba gave his talk before me, because he told us about the multi-line Q formula at t equals 0. So at t equals 0, multi-line Qs are a certain arrangement of particles. So here, my particles are going to be pairing from top to bottom instead of bottom to top, like what you saw in the previous talk. So the Ferrari-Martin algorithm that we just heard forces each particle to pair to the first one that is weakly to the right of it in the row below. But now, for general T, we're going to remove that restriction. And so now we're going to, so now we're going to allow particles to choose what to pair with in the row below, and that choice is going to come with a weight that is some polynomial, or some rational function in T. Okay, and so we have some arbitrary pairing of particles under some restrictions that I don't need to go into. And then the pairing determines the labeling of the particles. So the strings that start in row 3 are labeled 3, strings that start in row 2 are labeled 2, and so on. So just like in the Ferrari-Martin projection. And then we read off the state of the ASEP from the bottom row. So this is a projection onto the states of the ASEP. And so this multi-line Q corresponds to this state 3, 1, 0, 1, 2, 3, which we read clockwise from here. Okay, and then there's also a convenient way of representing this picture by just recording the positions of the particles in the columns of a tableau. So my tableau has columns given by the parts of lambda. So we have 3, 3, 2, 1, 1. So I have 2 columns of size 3, a 2, and 2 1s. And then so every string of particles is going to be mapped to a column in the tableau where we map the position of the particle in the corresponding box. So here we have a string from 2 to 6 and then to 6. So then we record 2, 6, 6. And so this is a way to associate multi-line Qs with the tableau picture. Yes, this is supposed to be a 4. Thank you. Okay, and so the weight of each multi-line Q is a monomial in X, which is going to keep track of the content in each column. And then T is going to count how many times did we violate the immediate pairing condition. So how many times did we skip over a particle that could have been paired with? And then Q is going to count the particles, the pairings that wrap around this lattice. So this is a new parameter that we didn't see before. Okay, and then James Martin's theorem is that the stationary probability of the ASEP is given by summing over all of these weights of multi-line Qs that project to the given state. And okay, so now let's look at this, this procedure in some more detail to understand what that weight is. So every ball is going to choose a particle to pair with in the row below, and it can wrap around as many times as it wants before it chooses the particle. And then the weight that we associate with that pairing is going to be T to the number of balls skipped times Q to the number of wrappings times something that we call the leg that we don't need to worry about. And so here, if we assume that the particle wrapped 3 times, or sorry, j times, then the weight in T is going to be 3j plus 2 because it has to skip at least these 2 balls, and then 3 are skipped every time it wraps. So if we sum over all possible ways of pairing these 2 particles, then we just get a geometric series. And then this is the term that corresponds to the weight of that pairing. Okay, and so we do this for each pairing. So we assume there's a certain fixed order of pairing of the particles, because now the order of pairing is going to give us different weights. And then we multiply them all together to get the weight of the multi-line Q. Okay, and so our theorem is that summing over the multi-line Qs with these weights gives us the full Macdonald polynomial. So what's really amazing is that we didn't really need to do anything to the object. We simply associated the X parameters with the column content, and then we associated the Q parameter with the wrapping, and then we just got Macdonald magically. So unfortunately, proving it was a little more complicated. Okay, so now let's talk about how to go from here to the modified Macdonald. So plethism is a type of composition of symmetric functions. So it has to do with compositions of representations of the symmetric group in GLN. So for a very simple example, so plethistic notation uses these brackets. So if whatever in the brackets is some polynomial, or sorry, some formal power series whose coefficients are 1, then the plethism of f of g is simply substituting the monomials in G into the variables of F. And so this can be extremely complicated in general. And so we define the modified Macdonald as the plethism of P with this geometric series. So when we expand x over 1 minus t inverse, we just get xi times all powers of t plus, so x1 times all powers of t plus x2 times all powers of t, and so on. And so that is what we plug into the p to get the h. Okay, so now remember that when we had a Macdonald polynomial with n variables, we represented that as a multi-line queue with n columns. So now we can try doing the same thing. So we naively write out infinitely many columns, which are labeled by these monomials that we get from the plethism. And then we put a multi-line queue in this picture. And then we compress it. So we allow all of the particles in the columns of type x1 to just be together in a column labeled x1. And same for x2 and x3. So now particles are going to be occupying the same site with multiplicity. So we went from the fermionic model to the bosonic model. And now notice that we have this T inverse here. So that simply means that we need to reverse the direction of the pairing, because T is counting skipped particles. So now when we invert the T, we want to count the particles that are not skipped. Okay, and then so we drew this picture, and then we conjectured that this would give us a modified Macdonald polynomial. And then we proved that it does with Arvind and James. And it also turns out that these bosonic multi-line queues with this projection also give a formula for the stationary probabilities of the TASR. Okay, so these become very difficult to draw and very difficult to keep track of the pairings. So now we're just going to represent them as tableau. And so we're going to record each string of particles as a column in the tableau, as I said before. And then the column content of the diagram becomes the monomial weight of the tableau. Okay, and we also notice something. So because there's no restriction on how many particles there are in each site, there's no restriction on how we fill this tableau. So now our objects here are going to be arbitrary fillings with integers 1 through n of this shape. Okay, and now in order to count to get the Q parameter, we need to look at the wrappings of these pairings. And so that corresponds to entries in the tableau that are larger than the one below. So we call that descent. That's the major index statistic. And then we also want to count these particles that are skipped by the pairings. So in the tableau, that looks like looking at these triples where we have 2 particles in the same column. So that corresponds to the 2 pairing with the 3. And then particle to the right in the column below, and that corresponds to the particle that got skipped over. And so if these integers are increasing in counterclockwise orientation, then that corresponds to a skipped particle. And so here's another skipped particle, and there's only 2 of them. So actually, there are 6 of them, according to this slide. So the weight of this filling is going to be this monomial, q to the maj, t to the quin. Okay, and so we have this formula for the modified Macdonald that is a sum over all possible fillings of this shape weighted by this q and t. Okay, and so this looks a lot like the Hagelin-Heyman-Lur formula that I showed in the beginning, except that this statistic is slightly different. And that becomes very critical in connecting this to the TASRB. Okay, so now we showed that the stationary distribution of the TASRB, the multi-species TASRB of type lambda, is given by the sum over all possible fillings, whose bottom row corresponds to the state weighted by this t statistic. And we proved this by explicitly constructing a Markov chain on Tableau that projects to the TASRB. And so we get that the partition function of the TASRB is a specialization of the H. Okay, so let me summarize what we've done so far. So far, we have a Q inversion Tableau formula for the TASRB and the modified Macdonald. And so now we would like to see if we can get the analogous formula for the ASEP. And so we use this technique called superization, which is combinatorial interpretation of plethism, to get a Tableau formula using the same statistic, but we call it a co-quin formula. Okay, so let me briefly talk about that. Okay, so these are just some manipulations of the plethistic notation. So let me get to the punchline. So we can write, so if we flip the plethism from applying it to the P, and then we instead write the P as plethism of H, then we end up with this very simple form where we plug in a positive alphabet and a negative alphabet into the modified Macdonald. So that's what this capital X and X bar represent. So what this means is that this is just the modified Macdonald where we substitute a new alphabet, which is positive and negative. And so doing that, we can just take the same Tableau formula, but expand the alphabet for our fillings. So we can now fill our Tableau with positive and negative integers, and then there's a certain weight associated to the positives and the negatives. And there's a weight-preserving involution that allows us to compress this formula and eliminate all of the fillings that have equal numbers in absolute value in cells that are in the same row or in cells in this configuration. And so those are called attacking configurations. So we end up with a formula in terms of non-attacking configurations where this is now a positive formula. And finally, we can compress this even further by summing over all fillings with the same absolute value. And that compression gives us this formula for the p lambda. So essentially, these coefficients represent all the possible choices of positive or negative letters in the filling. Okay, but notice that we have this prefactor here. So this prefactor is actually the t analog of all of the permutations that fix the partition lambda. So these are permutations of the columns of the fillings of lambda. And so the question is, can we compress this formula even further by imposing a certain order on the columns so that we can eliminate this prefactor?
Sorry, could you go back? I lost where the f lambdas appeared suddenly. So in this last formula, you have this f lambda inverse, but before that you did not? Did I miss it somewhere?
So the f lambda is...
Oh, okay, it comes directly in plethysm.
Yeah, because we have to apply the plethysm to the integral form of the p. So the f lambda is just a polynomial in Q, or a rational function in Q and T with integer coefficients.
And this thing you showed right now, this product of mi factorials, is that part of f lambda? Or
it is part of f lambda. So these terms are contained in the f lambda, but a lot of those terms are going to cancel with the things that appear here.
Okay.
So basically, we get rid of most of the f lambda by canceling them with these guys.
Okay.
But then there are some left, and those are those terms.
Thanks.
And so we did do the same thing with the HHL formula, but there wasn't the same cancellation because we needed these special terms with the special statistics to cancel correctly. Okay, so now the question is, can we just fix an order on the columns and sum over a smaller set of fillings so that we don't have all these permutations of the fillings? And so I was able to show that we can do that using a certain probabilistic column swapping operator. So it's an operator that allows us to exchange two entries in a column without affecting the rest of the weight of the filling. But because we need to preserve the non-attacking condition, this operator needs to be defined as a probabilistic operator. Okay, and so now let's define a sorted filling to be a filling where we just fix an order of the columns and we just make sure that columns of equal height have their topmost entries increasing. Okay, so here's the formula. So now we're just summing over a smaller set of fillings. The rest of the terms are the same. And we got rid of the prefactor. And so here's an example. So this is a sorted tableau. So here, the topmost entries of this row are all increasing. And this one tableau is going to correspond to all of these other tableaux with the same row content. So that's what our compression is accomplishing. And you might notice that there's only 6 permutations of these columns. but I have more than 6 tableaux here. But that's why we need the probabilistic operators. So here's a concrete example of how we can compute a single coefficient of this polynomial. So this is how, so we have 228 HHL tableaux. So that was the first formula I showed you in the beginning of the talk. Then there are 84 tableaux with this Q inversion statistic. But now if we use the compressed formula, then there's only 6 sorted tableaux that let us compute this polynomial, or this coefficient. Okay. So to summarize, so we have these 2 formulas. So we have using the same statistic, the Q inversion statistic, except that here the statistic goes in reverse. And then they give the probabilities for the ASEP and the TASERP. And then they also give the symmetric Macdonald and the modified Macdonald, and they are directly related to each other through superposition. So a few things that I wanted to mention. So first of all, the t equals 0 case of this picture is very beautiful because when there is no choice of pairings, we can simply associate a configuration of particles to each multi-line Q without keeping track of the pairings. And then the Ferrari-Martin projection map is what gives us the probabilities. And in that case, the multi-line Qs corresponding to ASEP are simply fermionic multi-line Qs, or fermionic configurations of particles, which we can think of as tensors of column vectors. And then the multi-line Qs corresponding to TASERP are bosonic configurations of particles corresponding to tensors of rows. And then we use the Ferrari-Martin map, or the pairing map, becomes simply the Nakashiki-Yamada rule. And the Q statistic that I talked about, which counts wrapping pairings, becomes the Nakashiki-Yamada energy function on those tensors. Okay, so a few questions that I still have. Okay, so first of all, the multi-line Qs that I showed you in my earlier slide are slightly different from the multi-line Qs defined by James Martin. And so the formula that I just presented directly corresponds to the multi-line Qs constructed by James Martin. So that gives an alternative multi-line Q formula for P lambda and also for the ASEP polynomials. So second question. So we can write formulas for the non-symmetric Macdonald polynomials using the same Hagelin-Heyman-Lurie statistics. But we see here that using our statistics, our slightly different statistics, actually gives a much nicer formula. So then I wonder if we can use our nicer statistics to get better formulas for the non-symmetric Macdonald. Okay, and my last question is to do with the non-symmetric refinement of the modified Macdonald. So the symmetric Macdonald, the P lambda, one way to construct it is in terms of the non-symmetric Macdonald polynomials, which can be obtained as eigenvectors of the Hecke algebra, of operators of the Hecke algebra. And so these operators are acting on the ASEP polynomials. And in the modified picture, we also have TASRB polynomials, which are the unnormalized stationary probabilities of the TASRB. And then we ask, are there operators that act on those TASRB polynomials in this modified version? And my feeling is that this might be very complicated because it would have to do with the action of the combinatorial R matrix in the fused model, which would have many more terms than the corresponding action in the fermionic model. So that is the end of my talk. And so since I have the honor of being the last speaker, so let's all thank the organizers of this really great conference. So thank you, Arvind, Ray, Ralph, Rinat, and Sanjay. Yes.
Thank you, Olya, for this great conclusion to the conference and also for assuming part of chair's duties. Thank you very much for that. Let us thank Olya again. And are there any questions?
Maybe I missed it. What is the exact formula for the Quinn statistic, co-Quinn statistic? Did you define it? Is it just?
It's exactly the same.
It's like Quinn, but in clockwise, or?
No. Yes. Right. So the Quinn statistic looks at all triples in this configuration, and it checks whether the entries are
anti-clockwise,
are increasing counterclockwise, and then co-Quinn is just the reverse of that. So we look at clockwise orientations of the entries. And
so just to understand this theorem, so you look at fillings where the Quinn statistic is 0. And
no,
it's a Quinn non-attacking, right? So
they're non-attacking means that we cannot have the same entry in these two boxes.
That's all.
And in the same row.
In the same row.
Yeah. So in the same, we can't have the same entries in the same row, and we can't have the same entries in adjacent rows. So that's what attacking means. And this actually has to do with the fact that, well, in the ASEP, we have this exclusion property where we only allow one particle per site. Yeah. So the entries in the row tell us the particles in the sites of that row. So if we disallow there to be 2 of the same particle in the row, we get the exclusion property.
I see. Okay. So there is also, so the fillings that you consider also could potentially have a non-trivial Quinn statistic, but.
Well, we do have.
So no,
we have the co-Quinn.
Right. But you don't count Quinn, right? You just count
Well, co-Quinn is just n of lambda minus. Okay, yeah. Okay. So co-Quinn is some constant depending on lambda minus Quinn. Okay. Because we just look at all the possible triples and then subtract the Quinn.
Okay. Thanks. Okay.
So a question. If you take particle systems, if you take a large size, probably there is some scaling limit, non-trivial scaling limit, and you have some probabilistic proof of your formula. Is it possible that usually in particle systems, the scaling limit maybe simplifies? Is it possible that there is some non-trivial scaling limit of your construction, which maybe, I don't know, simplifies?
So a very naive way for me to think about it is to have a multi-line queue on infinitely many columns. Is that what you're saying about the scaling limit?
Not necessarily. Yeah, this is one possible scaling limit, but maybe you can there are several scaling limits. Maybe non-trivial one.
Yeah, I guess the parts of lambda, you could look at a scaling limit for the parts of
For
lambda.
example, trajectories of particle might become Brownian motion, something like this. If, I don't know.
Yeah, so
I think in the continuous, this scaling limit of colored, of stationary states of colored models becomes something simple. I think they call it stationary horizons, so something like this is some Brownian motion that do something relatively simple. I don't know. Just
yeah, so that's very possible, but that would end up being some kind of limit of the Macdonald polynomial. And so I think there are people who work on that, but I don't actually know. Yeah. Maybe for certain types of partitions lambda, for example, a rectangular shape, you could get something nice, especially when q equals 0, because then it factorizes.
Well, if there are no more questions, let us thank Olya again. And since this is the last talk, we'll have a lot of clapping to do, so let's thank all the speakers of the conference. And last but not least, all the participants who stayed here and asked these nice questions. Right, yeah. So let us also thank all the people that helped this event to be a success, helping with videos, with everything in this nice facility.